pretty common in English words. But we disallow other crazy punctuation that does exist in some words, but isn't necessarily common. So we can solve, though, even more interesting problems here now that we have trees. So Morse code is something you're probably generally familiar with as a kid, and you can bang out messages using these dots and dashes or sounds that represent short dots or long dashes. But the problem with Morse code is that it's not immediately decodable. In other words, if I give you the sounds or I show you the symbol, let's say dot slash or beep beep, what did I just spell out? OK, you say A and you might be right, or ET. So Morse code is not immediately decodable because there's ambiguities that arise. If you have dot slash, could be a dot and a slash, or it could be dot slash or dot dash. So how did they solve this? Well, the military folks who would hit the little beep, 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 beep in the old movies, well, they would just pause, essentially, between words. Or you get good enough at it that you just realize that in context, obviously, you spelled the letter A, not ET. You just get good at it. But fundamentally, and certainly if a program were parsing this information, you need a split-second pause. What's the downside there? Well, even though Morse code is just dots and dashes, there's actually a third digit, which is pause, which is not pictured. If you need to kind of delay yourself, why is that bad? Well, it just kind of slows things down or leads to ambiguities. But it turns out you don't need these ambiguities. You can actually encode messages being very succinct, right? This is what's neat about Morse code is, relatively speaking, how short these sequences is. And yet all this time in CS50, we've been using 8 bits to represent every letter of the alphabet, whether it's a capital A for 65 or 97 for lowercase a. I mean, the Morse code folks, whittled this down, the letter E, to a single dot, which is effectively like a single bit. And it's no coincidence that E is pretty short, T is pretty short, I is pretty short, and yet Z is kind of long, and Y is kind of long. Because again, the dashes represent longer tones of sound. So what did they do? They optimized for the more common cases. E is pretty common, A is pretty common, so they have relatively shorter sequences than J or Y or Z. So this suggests some form of compression. And we don't seem to have learned from Mr. Morse here, whereby for ASCII and for computer encoding of letters, we've been using 8 bits this whole time. And the result of using 8 bits is obviously every letter takes up 8 bits. And so often, we're just wasting a lot of space, right? If the letters of the alphabet only go from 65 up to 26 plus that, and then 97 plus that, and you never use some of the crazy punctuation on the keyboard, let alone some of the non-printable characters, we're just wasting bits. So what could we do instead? Well, let's try using one of these data structures in sort of a novel way to compress information, and in turn answer the question, how do you actually compress information? When you use zip or the compress feature in Windows or Mac OS, like what is actually going on? Well, if it's a text file, it might very well be something like this. So let's come up with a completely arbitrary text just to have a simple discussion point. So this string here, ECA, is completely random. There's no pattern there. But what is noteworthy about it is that it's only composed of A's and B's and C's and D's and E's. And if you add up all the letters in that crazy long string, which would normally take up 8 bits times the length of that string, you see that 20% of the letters are A's, hence the 0.2, 10% are B's, 10% are C's, 15% D's, and 45% E's. So already, if we were going to reinvent the ASCII system and use fewer than 8 bits to represent each of these letters, A through E, which one would you probably want to use the fewest bits for, just intuitively? So E. So hopefully we can come up with a system, maybe using today's building blocks, that somehow gives us very short sequences of bits for E's. And OK, fine, we'll spend a few more bits on B's and C's than we would on A's or E's. In short, can we do better than ASCII? Can we compress information and thus save disk space? Well, let's try this. We have this ability now to talk about trees and also build trees using simple C structs. So let's go ahead and draw 5 trees, but 5 stupid trees. Trees that are only single nodes. So they're all leaves, they're all roots, but they are nonetheless trees. They just have no children, each of these 5 trees. And just to keep me sane, I'm going to put inside of each of these nodes its current weight, based on the original weight in the sentence. Now, just to be clear, even though we're about to compress something completely inane like this, now imagine this is actually a large movie script or the King James Bible or some huge body of English text that is nonetheless implemented with ASCII, just like this. And there, too, there's going to be patterns, right? The word the, pretty darn common in English. And there's definitely common letters like E and so forth. So even though this is contrived, there's definitely statistical patterns in English words. So here are my 5 simple trees. I want to go ahead and build one big tree out of each of these nodes. So you know what I'm going to do? I'm going to go ahead and combine the 2 smallest nodes possible at every decision point. So the smallest nodes right now are 10% and 10%, 0.1 and 0.1. So I'm going to go ahead and merge those into a new tree by creating a new root, updating its left and its right pointer to point to those guys. And again, to keep myself sane, I'm going to draw inside of the new node the total of the old node. So 0.1 plus 0.1 gives me 0.2. And notice, just because I kind of know where this is going, I'm going to start labeling the edges I'm drawing. I'm going to arbitrarily but consistently say a left child's edge or arrow just represents a 0 bit, and the right arrow represents a 1 bit, just because. So now let's repeat. So now let's combine 2 of the smallest. We actually have a little discretion here because I've got 0.2 as the root, 0.15 and 0.2 as the root. I'm going to go ahead and break this tie arbitrarily, but consistently. And I'm going to go ahead and combine that 0.2 on the left with 0.15 on the right, create a new node whose sum is 0.2 plus 0.15. So that's 0.35. And I similarly labeled the edges. And now, just to make sure we're all on the same page, what 2 nodes get combined next? 0.35 and 0.2, because those are both smaller than 0.45. So the picture is growing. And now realize I actually put the nodes in the right place so we get a pretty picture. But even if they weren't aligned in a pretty way, you would still get the same tree fundamentally. Let's now combine the final 2 nodes. And now I claim I have a tree. This is actually called a Huffman tree, named after a computer scientist named Mr. Huffman, who then proposed that using this policy of assigning 0 bits on the left edges and 1 bits on the right edges, you now have your own custom alternative to ASCII. What this system proposes now is that I'm going to start using, for the letter A, B, C, and D, and I'll switch over to the chalkboard in just a second, the following encodings. If I'm going to represent the letter A, or B, or C, or D, or E, I'm going to start at the root and figure out what pattern of bit gets me to it. So let's start with A. I start at the root. To get to A, I go left, which gives me a 0. Then I go to the right, which gives me a 1. So I claim henceforth, forget about this crazy 8-bit ASCII system. I'm going to use 2 bits for the letter A, 0 and 1. For the letter B, what pattern of bits will I use? Yeah, 4 zeros. Again, if not quite following, we start at the root. We just find B. And to get there, we go through a 0, 0, 0, 0. So B's encoding is going to be a little longer. Still better than 8 bits, but it's 4 bits this time. So C is going to be 0, 0, 0, 1, because I'm just following it, following the root down to it. D is going to be 0, 0, 1. And E, very nicely, is going to be 1. And now what's neat about this, and I'll put this on the screen, which maps that tree to numbers. What's neat about this is, 1, we've optimized for the really common case, followed by the next common cases. And we're willing to spend a few more bits on the less common cases. But unlike Morse code, notice none of these things are prefixes of one another. In other words, if I draw the numbers, let's see, 0, 1, 0, 0, 0, 0. What does this decode to? Well, notice there's no ambiguity. If I start with 0, could be any one of these. But if I then immediately see a 1, it can only be an A. And that's pretty compelling. There's no ambiguity, which means I don't need a break. I don't need to waste bits saying pause here, or here's a gap between letters. Now I see another 0. Could be any one of these. I see 2 zeros. OK, it could be any one of these 3. I see 3 zeros. I've now whittled it down to this. But then notice 4 zeros means, aha, this has got to be B. So by contrast, Huffman's coding scheme is immediately decodable, which means it is very efficient in that you don't waste bits or time in between letters. So what's the takeaway? Well, now the takeaway is quite simple. You can now encode A's and B's and C's and D's and E's with far fewer than 8 bits. But what's the gotcha? If you're going to actually encode letters in this different way, and you're going to kind of shrug off ASCII, what's the price you're paying? Because, right, if Mr. Huffman had this brilliant insight and we're still using ASCII, there's got to be a catch to this. So why are we not all just using this scheme?
If you have like 26 letters, the amount of bits is pretty big. So some are less than this letter.
Exactly, right? I'm kind of naively assuming, well, if my world only has A's, B's, C's, D's, and E's, well, I don't really need to use ASCII because I have such a smaller address space. So of course I can use fewer than 8 bits. But if you actually want to be able to let someone type any character on the keyboard, you're going to eventually need to start spending more bits. So what this really is, the takeaway really is that if you have patterns in your data, common letters or common words, you actually do have an opportunity then to compress data. And the fun thing about data is that there's almost always patterns, right? Even in things like music, there's choruses and parts of songs that repeat. And if you can leverage those commonalities and say, do I really need to store this chorus part of the song 3 different times just because the artist sings it 3 different times? Why not just store it once and then somehow digitally remember times 3? Which you can presumably express much more succinctly, we can then save bits that way. And in fact, we can. So just to be clear, these nodes we're now drawing, again, we can come up with kind of a simple C structure where we store the symbol that we're representing, the frequency as an int or as a percentage, as a float. We could do it either way, but generally, again, using ints instead of floats avoids issues of precision and accuracy. And then we need a pointer to the left or right. But let's now map this same idea not just to arcane text in A's, B's, and C's, and D's. Suppose we consider like the German flag here vis-a-vis, say, the French flag, which is nice in its simplicity too, in that whereas these guys have horizontal bands, these guys have vertical bands. Any thoughts as to which of these two flags, if stored as a GIF of an internet or file format, which one could compress more? They are the same size, even if I didn't quite resize them correctly. They're the same number of pixels. Which one might compress better? Now, the French, it's kind of nice, but this German's kind of redundant too, from left to right. Turns out you can't really know this unless you know the GIF specification, but there's opportunities here clearly to compress, right? Well, frankly, I could represent this flag with like 3 pixels and then just say repeat some number of times. Same deal for the French flag. Well, the authors of the GIF file format, GIF, decided that, you know what, just like in BMPs, whereby images are represented as scan lines from left to right, what we're really going to do is recognize that, all right, the top black band of this flag, let's just say that the top left pixel is black and then say repeat for the rest of the scan line. Then the next row, we say black, repeat, black, repeat, black, repeat. Then eventually we get to red, and then we just say red, repeat, red, repeat. So it turns out the French flag, if saved as a GIF, doesn't quite compress as well because you have to keep changing your mind. You have to say blue, repeat, oh, white, repeat, oh, red, repeat, and then again. So you're still compressing it, but you can't repeat as long chunks as possible because just somewhat arbitrarily, the GIF authors decided that we're going to compress images effectively laterally. But you can actually see this. So I downloaded these same images into a folder. And if you actually look at this, there's the same German flag. Here's the same French flag. So they look like the same size, but look at their file sizes and ignore the I's in the middle there. So the French flag is twice as big, 8 kilobytes. And that's simply because of how GIFs actually compress. We can apply these same ideas, independent of these tree structures indeed, whereby we can have, say, a picture of this apple. Right? This apple, if stored as a GIF, you do need some red and brown to represent the stem and the apple itself. But this blue background, you definitely don't need to remember all of those pixels. Instead, just remember some of them and then say repeat wherever it's white. Or in the context, perhaps more modernly, with movies. So this is just a little cartoon of 2 scenes in a movie where on the top strip of film there, notice the little RV, the truck, and the house, and the tree. Now, in this simple little cartoon movie, the car is moving from left to right, but what's obviously not going to change? Well, the tree's not moving, and the house isn't moving. The background's not changing. And so what can you do? Well, actually, in this case, the car, OK, so some of those things were moving. The tree and the house were effectively moving as the camera moved, but the sky was not changing. Right? So you can do the same thing. Throw away information that's not changing, because you definitely don't need to store in a movie the same picture again and again. And for those unfamiliar, a movie, a video, is pretty much like a bunch of images back to back to back to back to back, played really fast so it looks seamless. And here too, in the bottom, you're seeing the same idea, where you can do inter-frame compression, whereby, you know what, if we know the car is starting over there on the left, and then it's going to end up there over on the right, do we really need to watch as the car does this? Or can't we, with algorithms, kind of predict where the car is going to be, and then throw away what might otherwise be useless information. And you can see it here too. So this is a picture on top of an uncompressed video of a bee flying over some flowers. And in the bottom you see, well, if the flowers aren't changing, only the bee's moving, let's just throw away the background, throw away the purple and the blue, and just keep track in our file where that bee actually is. So where are we going with all this? Well, we now have the ability to have images. You have